You have probably heard statements of the form if P then Q or P if and only if Q before. In this video, we will take a look at the truth tables for these types of statements. We begin by defining a conditional statement. Let P and Q be statement variables. Then the conditional from P to Q, written as P with an arrow to Q and read as P implies Q or if P then Q, is defined by the following truth table. Note that P implies Q is false only when P is true and Q is false. If we have a statement of this form, we call P the hypothesis and Q the conclusion. Let's think about an example of a conditional statement. Suppose I make the following promise to you. If you do your homework, then you get a chocolate. Now, in which of the following scenarios can you say that I spoke falsely to you? In scenario A, you do not do your homework and you get a chocolate. In scenario B, you do your homework and you get a chocolate. In scenario C, you do your homework and you do not get a chocolate. And in scenario D, you do not do your homework and you do not get a chocolate. Recall that by definition, an if-then statement is false only when the hypothesis is true and the conclusion is false. This happens in scenario C, where you do your homework and you do not get a chocolate. Only in scenario C are you justified in saying that I spoke falsely to you. A conditional statement can also be expressed using other logical connectives. In particular, P implies Q is logically equivalent to not P or Q. We will set up the truth table with all possible combinations for true and false values of P and Q, and then we will record the truth table for not P. Now let's fill in the truth table for not P or Q. There will be only one row where this is false. This will happen when not P is false, as well as Q false. This happens in the second row, so we can fill in false there and true everywhere else. Next, we recall the definition of the truth table for P implies Q. It will only be false when P is true and Q is false. It will be true everywhere else. Since these two statement forms have identical truth values in every row of the truth table, we know that they are logically equivalent. This means that we can write the statement, if you do your homework, then you get a chocolate, equivalently as either you do not do your homework or you get a chocolate. As another example, the statement, if Jill forgets to wear sunscreen, then Jill will get a sunburn, is logically equivalent to the statement, either Jill does not forget to wear sunscreen or Jill will get a sunburn. In English, we would often say this as either Jill remembers to wear sunscreen or Jill will get a sunburn. When working with conditional statements, a term you will hear a lot is the contrapositive. Here's the definition. The contrapositive of the statement P implies Q is not Q implies not P. Moreover, these two are logically equivalent. In other words, P implies Q is logically equivalent to not Q implies not P. We can check this with a truth table. We will record the truth values of not P as well as not Q, then recall the definition for the truth table of P implies Q, and finally, let's write down the truth table for not Q implies not P. Notice that this will be false only if not Q is true and not P is false. This happens in the second row of the table, so we can put false there and true everywhere else. Therefore, we see that the two statement forms are logically equivalent. Revisiting our example from before, we can say that the statement, if you do your homework, then you get a chocolate, is logically equivalent to, if you did not get a chocolate, then you did not do your homework. Now that we are familiar with conditional statements, we should know how to negate them. The negation of P implies Q is logically equivalent to P and not Q. As usual, this can be proved using a truth table, but here we will provide a proof using rules of logical equivalence. First, we will write down not P implies Q. Then we can rewrite this as not P or Q, because we recall that P implies Q is logically equivalent to not P or Q. Now we have a negation of a disjunction, and so we can use De Morgan's law to write this as not P and not Q. But of course, not P is logically equivalent to P. This means that our statement form is logically equivalent to P and not Q. As an example, let's write down the negation of the following conditional statement. If today is Monday, then tomorrow is my birthday. The negation of this is, today is Monday, but tomorrow is not my birthday. Notice that here I've used the word but instead of the word and. In English, we often use the word but to mean and when what follows is a bit of a surprise. Next, we will define a biconditional statement. Let P and Q be statement variables. The biconditional of P and Q, denoted P double arrow Q and read as P if and only if Q, is defined by the following truth table. Note that P if and only if Q is true when P and Q have the same truth value and false otherwise. Also observe that P if and only if Q is logically equivalent to if P then Q and if Q then P. You can check this yourself using a truth table. Now we will review some various ways of saying a conditional or biconditional statement. The following are equivalent ways of saying P implies Q. We could say if P then Q, or P implies Q, or P is a sufficient condition for Q, or Q is a necessary condition for P. And here are some equivalent ways of phrasing a biconditional statement. P if and only if Q, P is a necessary and sufficient condition for Q, Q is a necessary and sufficient condition for P. It is very important to know what somebody means when they say necessary condition or sufficient condition, or necessary and sufficient condition. Now that we have learned the logical connectives of the conditional and the biconditional, we should review our order of operations. First, apply negation. An equal second is and or, and as equal thirds is the conditional and biconditional. Remember, if in doubt, use brackets to emphasize what you mean.